Hi guys, this is chapter 3, Uniform Circular Motion. In this chapter, we're going to talk about a concept that object is undergoing circular motion. It is undergoing uniform accelerated motion by maintaining the magnitude of velocity constant while the direction of the motion is constantly changing. Here are key concepts of this chapter. After completing this chapter, you should be able to distinguish between inertial and non-inertial frame of reference, analyze uniform circular motion and derive equation for it, investigate forces and acceleration experienced by the object in a uniform circular motion, and conduct inquiries and analyze technologies that applies those principles. And this is section 3.1, inertial and non-inertial frame of references. We already defined the frame of reference before when we talk about forces. So frame of reference is a coordinate system relative to which motion is described or observed. However, we're going to focus on type of frame of reference. Before, we talk about frame of reference that is stationary. But there's more than this. In a relative motion, we touch this concept a bit. However, we're going to focus on types of reference frames or frame of reference. We have two types, inertial and non-inertial frame of reference. Let's start with the easy one, which is the inertial frame of reference. Inertial frame of reference is a frame of reference that is at rest or move at a constant velocity. So it gives you an idea of the first Newton law. So that's why the law of inertia holds on this inertial frame of reference. If you are inside of the inertial frame of reference, there is no physics experiment that you can conduct in order to distinguish between stationary frame of reference or frame of reference that is moved at a constant velocity. More about this, you're going to learn more in a relativity theory of Einstein. To understand the inertial frame of reference, we can analyze the motion of the bus and the ball on a bus floor. When the bus moves at a steady speed without changing its direction or a constant velocity, you might not be aware the bus is moving. We talked about that on relative velocity when we saw that when you are inside of the train or a bus or inside of the airplane, as long as they are moving at a constant velocity, you cannot feel that difference as they are moving at a constant velocity or they are stationary. So if you have a bus and you have a ball in the floor of the bus, you see that the ball is not moving relative to bus. So velocity is zero. If the ball is not moving and a bus is not moving, that is the same for the person that is inside of the bus and for a person that is outside of the bus. They see the same thing. Ball is not moving. Velocity is zero. However, if bus is moving at a constant velocity, ball will not move. So relative to bus, ball is still stationary. However, for the person that is outside, that ball is moving with the bus with constant velocity. However, there is one thing. Acceleration is zero. So no net force acts on a ball. As a result, there is no reason for the ball to change its state. As we mentioned in a relative motion, the person in a bus or in a train or in an airplane and the person outside on a ground see the motion differently because they are in different frame of reference, different point of view. So for the person in a bus, the ball is not moving, so velocity of the ball is 0. For the person outside, the velocity is constant because the ball is moving with bus. However, in case of the bus moving at constant velocity, that means inertial frame of reference that is moving at constant velocity, both persons inside of the bus and outside in the ground, they have one thing in common. Acceleration is 0. Acceleration of the ball is 0. So the ball either is stationary or is moving at a constant velocity. So similar to the first Newton law. So that's why it's called inertial frame of reference. So inertia, inertial frame of reference. Another type of frame of reference is non-inertial frame of reference. As you may have guessed already, non-inertial frame of reference is a frame of reference that accelerates with respect to an inertial frame of reference. So it accelerates relative to a stationary frame of reference or to a frame of reference that moves at a constant velocity. So law of inertia does not hold. Let's continue with that experiment. Now the ball is on the same spot, but the change here is the bus will accelerate. So if bus speeds up, that means change in acceleration, change in motion, then what is going to happen? Because all objects that do have mass, have inertia, they try to resist the change in motion. And since the ball is on that floor, can roll back, and that's pretty much what happened. And we already talked about this when we talk about inertia. When the ball on an airplane rolled back, same thing happened on a bus this time. So velocity will increase, acceleration is forward, then the ball will try to keep the previous state and is going to roll backward. Now, if the bus this time is going to slow down, what is going to happen? If the bus will slow down, a person on a bus frame of reference will see the ball moving forward, is accelerating forward. So it's going to move forward to keep that same state of motion as before, because acceleration was backward, it's slowing down, it's braking. So the speed or velocity is going to decrease in magnitude, but ball is free to roll, so it's going to keep the same velocity as before. The same thing will happen on a ball when the bus will turn a corner. That means that if the bus maintains the magnitude of velocity but direction changes, that means still bus is accelerating. It is on a frame of reference that is accelerating. So that means the ball, it is still on that surface on the floor of the bus, but is still on a non-inertial frame of reference. As a result, you're going to see that two people are going to see the ball is accelerating. From the person here, they are going to see the ball is moving sideways. So it's going to move in that direction, sideways. So the person that is sitting here, it sees that ball is moving not straight anymore, not stationary, but is moving sideways. As a matter of fact, that ball is not moving sideways. Ball is moving at a straight way, at a direction before it turns. So the ball continues moving at the same direction as a bus before the turn. Because of inertia, it's going to move at a straight line. So straight line means in a bus it is sideways. So that's how it's going to be. You may have experienced something like this, that when you are inside of the car and that car is turning a corner, you'll feel the push that makes you lean at the same direction as the direction of the car before the turn. Is this force real? Not really. It is just inertia that makes an object to resist the change in motion. And this time, the change is not a magnitude of velocity, but is direction of the velocity. From your point of view in the bus, which is accelerating, so it is non-inertial frame of reference. This would be like a force pushing the ball in a direction opposite to that in which the bus was turning. The same thing can happen to us. So our body is being pushed when the car is turning the curve. So as a matter of fact, there's no real force acting on a ball. It happened, as I mentioned, because of inertia. Now, fictitious force is an apparent or a non-existent force that is invented by physicists in order to explain the motion of the object within an accelerating or a non-inertial frame of reference. So fictitious forces simply explain non-accelerated motion in an accelerated frame of reference. Now we have a practice problem that we calculate the acceleration of non-inertial frame of reference. A teacher suspends a small cork ball from a ceiling of a bus. When the bus accelerates at a constant rate forward, so that means is accelerating, so that means bus frame of reference is non-inertial, is accelerating relative to ground, which is inertial frame of reference. The string suspending the ball makes the angle of 10 degrees with vertical. So the word spring suspending the ball, that means that the ball is not moving. It is bended at a 10 degree with vertical, but is like fake stationary. Calculate acceleration of the bus. So free body diagram is a tension and gravity, and that means we can resolve that tension in two components. Then, since that is suspending, that means it is looks like in equilibrium. So that has to be a force in order to cancel the x component of that tension, because y component is canceled by gravity. However, that is not normal. We are in a non-inertial frame of reference. So that means a frame of reference that is accelerating. So that x component is made or is created because of that acceleration. Because if the bus was not accelerating, is stationary or is moving at a constant velocity, that means that that cork is going to be vertically hanging. So the tension would be vertical. However, since that is accelerating, the ball, because of inertia, has a tendency to stay stationary, but since that is tied up by a string and is tied to a bus, has to follow up. So that's why it's following the bus. It is a little behind that change in motion. That's how you do it. That's how you calculate it. So that means that there is no such a thing as a tension on that direction. It is unbalanced force. So that's on that unbalanced force, we can calculate what caused that unbalance. That is acceleration. So on a y-axis, there's balance because there's no moving is no acceleration up or down. So we can say the y component of that tension is equal to force of gravity. But that y component is adjacent for that triangle. For this triangle here, this y component, which is on that side as well, it is adjacent of that angle, it's beside that angle. So we can say Ty is equal to T cosine theta. Then we can solve for tension, which is Ty over cosine theta, or Ty, it is already force of gravity, we already know. That is Fg divided by cosine theta, and we replace the Fg with the mg. Then tension, we can say that is mg cosine theta. That is important because it is going to serve us later on an x component. On x component, you have only one force, and that is responsible for that acceleration. As a matter of fact, that component is caused by acceleration. So then we can solve for tension x component, which is t sine theta, because it's opposite of that angle. Then we can say, since that tension was equal to mg divided by cosine theta, we replace tension here with mg cosine theta. So m and m cancel, and that would be expected because acceleration will not depend on a mass of the cork. That is equal, now A is equal to g sine divided by cosine, but as we know, sine divided by cosine is tan, so A is equal to g tan theta. Now we know g is 9.8, and we can calculate tan theta, and now we can calculate acceleration of the bus just being inside of the bus without stepping outside, being inside of the non-inertial frame of reference. Just by looking at that angle of that bending string that is holding a cork, you can calculate acceleration of non-inertial frame of reference, which is an accelerated bus. Now let's see the apparent weight from the reference point, from the frame of reference. As you stand on a bathroom scale, the magnitude of force of gravity, it is cancelled by a normal force. So we can say the normal force is equal to force of gravity. So reading on a scale is your force of gravity, is your weight. Based on the first Newton law of motion, this would be the same if you are in an elevator moving at a constant velocity or not moving at all. So normal force has to be equal to a force of gravity. So elevator is not accelerating. So that means you are in an inertial frame of reference. So law of inertia applies. Law of inertia holds. That means if the elevator is stationary or moving at constant velocity, normal force or reading on a bathroom scale is equal to your force of gravity or your weight. So what will happen if that frame of reference, elevator in this case, is accelerating, is becoming a non-inertial frame of reference? Then you're going to see apparent weight, which is not equal to your weight, apparent force, which is not equal to a gravitational force. If elevator accelerate upward, then a reading on your bathroom scale is going to be bigger than force of gravity. That means it's going to be bigger than your weight. If the elevator accelerates downward, then the reading is going to be less, so you're going to feel lighter. So that apparent weight or fictitious force is affecting the reading on your bathroom scale. So it is affecting your weight, your feel of the weight. So it is indicated in a reading of the bathroom scale or normal force. If you are accelerating downward at a rate of gravity, at a rate of 9.8 meters per second square, that means you're feeling weightless because there's no reaction. There's no force that is holding you. There's no normal force as you and bathroom scale and the elevator or anywhere you are, it is moving at a constant acceleration downward at 9.8 meters per second square. So that means nothing is holding you. So as a result, there's a different force that is up here in the reading of the bathroom scale, it is different normal force, and is going to be a different reading for your weight. In this case, it's going to be weightless. So reading is going to be 0. And you feel this when you run a roller coaster. You're going to feel weightless at the top of the roller coaster, and you're going to feel heavier at the bottom of the roller coaster. And we're going to learn this in a detail when we talk about circular motion. Let's illustrate the apparent weight with an example. A student with a mass of 55 kilograms stands in an elevator that accelerates. Determine the student's apparent weight, or a normal force, during each acceleration. A. Elevator accelerates upward at 2 meters per second square. We draw free body diagram. So Fg and Fn is moving upward, so that is acceleration is up, and positive direction has to be up. So it's a y-axis is accelerating, so that means F net y is equal ma. Then F net y is equal sum of all forces, we have just 2, is equal to ma. And now since that we have positive up, Fn is positive, Fg is negative. So we solve for Fn, we move Fg to another side of the equation, becomes positive. So Fg plus ma. So Fg is mg plus ma, we factor m. It is g plus a. And then you plug numbers there, 55 kilogram times 9.8 plus 2 meter per second square. So the answer will be 649 Newton. Now, let's say that elevator is accelerating downward. Same rate, just for simplicity. We draw free body diagram. Now it's moving up, moving downward. So the down is positive direction, which is the direction of the acceleration. And we do the same thing, similar to up. The only thing you have to pay attention to a sign, which is down. So F net y is ma, because it's accelerating. And F net y is equal to sum of all forces, is the same thing. Now we have to follow positive direction, which is down. So Fg is positive, and Fn is negative, is equal to ma. We can solve for Fn, which is Fg minus ma. So Fg is mg minus ma. We factor m, g minus a. Then we can plug numbers. 55 kilogram times 9.8 minus 2, that is 429. If you take a look, the acceleration upward, you feel heavier, and acceleration downward, you feel lighter than normal. But what is normal? A student normal weight is when there is no acceleration, when F net is 0, when the forces are balanced. So that means, based on the first Newton law, the student is moving at constant velocity or not moving at all. So to solve it, as always, we draw a free body diagram. We have two forces, Fg and Fn. Since that is in equilibrium, we just keep it traditional, positive up. Then we apply first Newton law, not second, first Newton law, because F net is 0. So F net y is equal to 0. That means sum of all forces is equal to 0. So Fn and Fg has to be 0. Then we follow the positive direction, even in first Newton law. So if we follow the same steps, we will never make mistake. So Fn is positive, Fg is negative, is equal to 0. So then we move Fg to another side of the equation, becomes positive. And we know that Fg is equal to mg, and we have m and we have g. So we plug those numbers and find the Fn is 539 Newton. So that is a normal weight. That is a force of gravity without acceleration. Okay, so next one, what will happen if the student will free fall? Let's see. We draw a free body diagram as always. So we have two forces, Fg and Fn, and acceleration is going downward. That will be a positive direction. So we follow the same step. Fny is equal to ma. Why? Because it's accelerating. It's a second Newton law this time. So F net y is equal Fn plus Fg. Those are two forces. Is equal to ma. Again, we follow the positive direction. Is down this time. So Fg is positive. Fn is negative. Is equal to ma. And acceleration is always positive. And we keep it like that way to make it easier and not confusing. And Fn is equal to Fg minus ma. We know Fg is mg minus ma. And we can factor m, and what is left there is a g minus a. Then we plug numbers. Thing is that g is 9.8 and a is 9.8. So it's 0. 0 times 55 is 0. So that means the normal force is 0. So although we draw, and we did the right thing to draw a normal force, in a free fall there's no normal force because nothing is holding anything. Everything is falling at the same rate. So that's why it's exactly what we actually mentioned before. There's no reading on a bathroom scale because, or no tension on an elevator cable, or no normal force on a bathroom scale holding you, or a elevator floor holding you, because everything is falling at the same rate. So that means nothing is holding. This is a practice problem that includes first and second Newton law, and it is an application of the apparent weight. Rope A is tied to block 1, and rope B is attached to both block 1 and block 2. The mass of block 1 is 4.2, and the mass of block 2 is 2.6. You lift both blocks straight up. Calculate the tension in the rope when the blocks move at a constant velocity of 1.5 meters per second up. So what is given? Mass 1 is 4.2, mass 2 is 2.6 kilogram. Acceleration is 0. How do you know? Because it's a constant velocity. In constant velocity, acceleration is 0, F net is 0. And then tension at the rope A is required, and tension at the rope B is required. Okay, so we can draw a free body diagram that includes rope A. So rope A is pulling both block 1 and block 2. That's why it's easier to actually draw a force of gravity for both of them, both masses. Now, choose a positive direction because it's moving up. Then sum of all forces on a y-axis is equal 0. So we have two forces, TA and Fg total is equal 0. We can choose that positive direction to be a T1 minus Fgt is equal 0. So TA is equal to Fg total, or is equal to mg total. And now TA is equal, total mass is equal sum of two masses, 4.2 plus 2.6. And G is 9.8 Newton per kilogram. So kilogram and kilogram cancel. So what we got, tension at A is 66.6 Newton. Now for tension on rope B, so rope B is actually pulling only block 2. So you do pretty much the same thing, but this time as a force of gravity has to be Fg2 only. Okay, then you do pretty much similar to what you did before. Sum of forces on y is 0. Then how many forces do we have? We have 2. We choose the positive direction up. And then TB minus FG2 is equal to 0. So tension on rope B is equal to FG2 is equal to M2G. And we can plug those numbers in that equation and we get tension at B is equal to 25.5 Newton. Okay, B, when blocks accelerate at 1.2 meter per second square up. This is a little bit more challenging because now we have a second Newton law we have to apply because acceleration is not 0. Acceleration is 1.2 meter per second square up, and up is positive, so that means 1.2 is going to be positive. But we do pretty much the same thing. We draw a free body diagram for tension T1A and total force of gravity, which include both blocks because rope A pulls up, accelerate upward, both of them. Then direction of the acceleration is up, and that will be a positive direction. Next one would be apply a second Newton law this time on a y-axis. So sum of all forces is equal to MTA. So how many forces do we have? 2. TA and FG total is equal to MTA. We follow positive direction, so TA minus FG total is equal to MTA. So TA is equal to, we move FG total on another side of equation, and that becomes positive. So TA is equal FG total plus M total A. We factor MG total because FG total is equal to M total G. So M total G plus A. And then we are ready to plug those numbers, and we get 74.8. We do a similar thing for rope B. So free body diagram. This time FG2, because rope B, as I said before, pulls only block 2 and accelerate upward. So that will be a positive direction as well, up. And we do exactly the same. So sum of all forces is equal to M2A this time. So how many forces do we have? TB and FG2 is equal to M2A. Now we follow the positive direction. So TB is positive minus FG2 equals to M2A. Then FG2 is equal to M2G plus M2A. We factor M2 equals M2 times G plus A. And we are ready to plug those numbers now. And the last one is plug those in the calculator, and we get TB is equal to 28.6 Newton. Here is an interesting problem to solve. There is a box that is holding a pulley, and a pulley is making the mass 1 and mass 2 to roll. In normal circumstances, if the mass 3 is stationary, then mass 1 is being pulled by mass 2 and is going to accelerate toward right, and mass 2 is accelerating toward center of the earth, down. However, there's a very interesting combination now. When applied force is going to accelerate all three of them, if you see that they are all connected, so you cannot really accelerate one and you leave the others, we can accelerate in a way that mass m1, which will accelerate because it's pulled down by gravity, and mass 3 is going to accelerate at the same rate, so relative to each other, both accelerated objects will appear to not accelerate, to not move, to not slide. So Mass 1 does not slide with respect to a frictionless surface when the horizontal force showing is applied. Determine the magnitude of horizontal force. So, what we have here, the solution for this is how to match the acceleration of all masses caused by an applied force Fa with acceleration of m1 due to a tension pulled by a gravitational force of m2. This is how we solve the problem. Let's do one at a time. We know the acceleration caused by applied force is equal to sum of all forces, which is applied force in this case, has to be equal to a total mass of all three times acceleration. From here, we can calculate acceleration, which is Fa divided by all three masses, because they are together. They are pulled or pushed in this case by applied force. Now, this has to be matched by acceleration that is caused by m2 pulling m1. So gravity is pulling m2, and since that m2 is connected by a rope with a m1, it is being accelerated on a right side as well. And this applied force is accelerating all three of them at a right direction, on a right side. So this one actually is going to be sum of all forces on x-axis is equal to m1a, because that is the tension that is pulling m1 on right direction. Then we can say m1a is equal to tension, but tension itself is equal to m2g, because that is being pulled by gravity. M2 is being pulled by gravity. However, as I said, it will appear that M1 is not moving relative to M3. So that means that M2 will never fall down. So it will never accelerate downward. So M2 will not be part of that acceleration sideways on a horizontal direction. So that's why we calculate acceleration caused by m2, because of the gravity, is equal to m2g, which is force of gravity of the mass 2, divided by mass 1. Now both of them has to accelerate at the same rate, otherwise m1 is not going to be accelerating at the same rate with m3, so that means either it's going to slide forward or backward. But that's not a condition. We don't want that object m1 or block m1 to slide with respect of the block m3. Now, both those accelerations are the same, and we can make that the right side equal as well, because the left is equal. So we can write m2g divided by m1, which is this acceleration here, has to be equal to this acceleration, Fa divided by m1 plus m2 plus m3. So from here, we can calculate Fa, which is m2g, open bracket, m1 plus m2 plus m3, close bracket, divided by m1. Then we have everything to solve the problem. Then you can plug those numbers in a calculator, and we can find the applied force is 39 Newton. Now it's your turn to do some practice to find acceleration of non-inertial frame of reference. You use a string to suspend a cork ball with a mass of 22 grams from a ceiling of the moving speedboat. The ball and the string hang at an angle of 32.5 degrees from vertical. Calculate the magnitude of the speedboat acceleration. Do you need to know the mass of the ball to make that calculation? Yes or no, and explain why. And here is the answer. You can pause the video, try to do it yourself and see if you get the same result. And second one, B, is determine the magnitude of tension in a string, and this time, do you need to know the mass of the ball to make that calculation? And you can explain yes or no, and here is what is expected answer for this. You can pause the video, try to practice, and see if you get the same result. And that's about it for this section 3.1. Have a good one.